6.4 The Wave Nature of Matter. Louis de Broglie postulated that if light can have material properties, matter should exhibit wave properties. He demonstrated that the relationship between mass and wavelength was wavelength equals Planck's constant divided by mass times velocity. Sample exercise 6.5, matter waves. What is the wavelength of an electron moving with a speed of 5.97 times 10 to the 6 meters per second? The mass of the electron is 9.11 times 10 to the negative 31st kilograms. We are given the mass and velocity of the electron, and we must calculate its de Broglie wavelength. The wavelength of a moving particle is given by equation 6.8, so it is calculated by inserting the known quantities h, m, and v. In doing so, however, we must pay attention to the units. We're going to use the value for Planck's constant in joules seconds, 6.626 times 10 to the negative 34th. We will recall that 1 joule is equal to a kilogram meter squared per second squared, and therefore our mass should be in kilograms and our velocity in meters per second. All the units will cancel out and leave you with meters. Our wavelength is then 1.22 times 10 to the negative 10th meters, which is then converted to nanometers and then angstroms. By comparing this value with the wavelengths of the electromagnetic radiation shown in figure 6.4, we can see that the wavelength of this electron is about the same as that of an X-ray. Practice exercise. Calculate the velocity of a neutron whose de Broglie wavelength is 500 picometers. The mass of a neutron is given in the table inside the back cover of your text. Be sure to watch your units. The uncertainty principle. Heisenberg showed that the more precisely the momentum of a particle is known, the less precisely is its position known. In many cases, our uncertainty of the whereabouts of an electron is greater than the size of the atom itself.